something? Is that where, or did people just go off on holiday early? Yeah, off on holiday. Yeah.
It's today's Lewis structure weekend, right?
Yeah, today's Lewis structures. So we're going to talk about Lewis structures. Okay. And so we did. There are actually points for this lab. The points are going to be when we start building the models. It's going to come a little bit later. So we did bicarbonate. The next example we're going to do is nitrous oxide. Into nitrogen has pretty rich redox chemistry. Nitrogen, the charge varies from what to what? The oxidation state. Well, you would look up on the periodic table what the oxidation state varies from. And nitrogen can vary from, well, it has normally 5 valence electrons, so it could go up to 8, which would be -3, or it could go to +5, which would be like helium. And so nitrogen varies from -3 to +5, that range. And what you see compounds ranging from -3, like ammonia or ammonium, and have nitrogen in the -3, to +5. +5 would be nitrate. And then you have a variety of compounds in between, including the element, which is at 0 oxidation state. So what types of compounds will we have here? Well, one type of compound that we could have are the oxides of nitrogen, NOx. And so X can take on different values, including an X equals 1.5. When X equals 1.5, then we have, is that right? Is that right? From N2O. Actually, that's not right. X would be 0.5, sorry. So NO 1/2, double everything, so we get N2O. Okay. And so this is called nitrous oxide, and the oxidation state in nitrous oxide is +1 for nitrogen, -2 for oxygen. And then we have, excuse me, NO2. Actually, before NO2 we have NO, and so we go from N2O to NO. This one had a name, nitric oxide, and it's got a +2. And so usually the ALS refers to lower oxidation state, the IC ending refers to higher oxidation state. The problem with nitrogen is it has many, many oxidation states. And so this nomenclature system doesn't work very well if you have more than 2 charges. We do. For example, we could have NO2. NO2 would have +4 for the nitrogen. And so what should we call this? Well, we've already used the IC for the NO. And so on this one, we'll have to call it nitrogen and just use its systematic name, dioxide. In fact, the systematic name is better because, this would be dinitrogen monoxide, nitrogen monoxide here. Well, anyway, we're focusing on nitrous oxide here. And so let's take a look at the structure for nitrous oxide. Lewis structure. Let's follow the rules here. And so for nitrous oxide, we have 2 nitrogens. It's going to give us 10 electrons, 2 times 5. And then 1 oxygen, that gives us 6 electrons. And so altogether, we'll have 16 electrons. The next thing we do is we take a look at the skeleton. And so we can come up with 2 skeletons here. This one looks very symmetric, NON. That's one possibility. The other possibility is an NNO. Now, normally we want the least electronegative element in the center. the least electronegative would be like a nitrogen. But one thing about oxygen is oxygen doesn't mind bridging two other atoms. So for example, in water, it would be HOH. And so oxygen naturally occurs as a central atom. So it's not unusual to have oxygen in the center here. We call it a bridging oxygen. Here, this is good, but this isn't the symmetric. I mean, this is the least electronegative nitrogen. And so let's just start off with this skeleton, the NON skeleton, and then see where that leads us. You know, if you're rushed for time, what you do is you normally put the least electronegative element in the center, which would be nitrogen. But in this case, we're okay. So we'll go ahead and complete the octet to the outer atoms, which would be the nitrogens. And when we do that, we've used up all 16 electrons. And so we don't have any electrons left over to place on the center. So when that happens, we have to create multiple bonds, like a double bond, a triple bond. And so here, we can increase the number of electrons in oxygen by taking a lone pair and forming a double bond here. So I'll take a lone pair, and that's going to lead to this structure here. All right, oxygen is still short of an octet. You know, when we count octets, we look at, you know, the total number of electrons surrounding, 2, 4, 6. And so we need 2 more. Well, it just makes sense to take the electrons off the other nitrogen and place them down here, and we end up with this. Okay, now everybody has an octet. And so does this look good? It looks good from the standpoint of the octet, but there's another thing we have to check, and the other thing we have to check is formal charge. Does this look good from a formal charge perspective? It looks good from an octet perspective. But when we look at the formal charge, let's count them. 1, 2, 3, 4, 5, 6. This is a negative formal charge here. This is the same. This will have a negative formal charge. 1, 2, 3, 4. This will have a +2 formal charge. Okay, when you read the formal charges, you read it like this, is because this is how the electrons were divided up. And so if you have a pool of 16 electrons, then the 2 nitrogens picked up extra and the oxygen lost 2. Does that sound right? You know, if we had a pool of electrons, 16 electrons, and you just said, okay, nitrogen and oxygen, take them, do you think that's how they would take them? That is, the nitrogens would beat out the oxygens and get extra electrons. Not really. I wouldn't think that, because oxygen is more electronegative than nitrogen. And so the formal charge looks unusual, and one, because nitrogen got an electron over oxygen. In fact, oxygen lost. And 2, this is kind of a high formal charge, because, you know, when we look at the electrons, well, electrons, oxygen came out short. And it's +2. Well, +2 formal charge is like a +2 charge, which means that essentially lost 2 electrons. Losing 2 electrons would be like I2. You know, I1, I2. I2 is about double what I1 is. And so this does not look good. The formal charges don't look good here. And so even though the octet looks good, the formal charges are bad, or high. High formal charge means, you know, a lot of charge separation. There. Well, you know, what we could have done is, instead of making 2 doubles, we could have made a triple and a single. And so what we could have tried alternatively to and see if this makes any difference is take another pair here. And so it looks kind of asymmetric. And the 2 nitrogens should be the same, so this doesn't look so good either. But we'll try it and see if that improves the formal charges. And so looking at this, this should be an oxygen here. Looking at this, I got 1, 2, 3, 4, 5. So the formal charge is better on this nitrogen because it's a 0 now. 1, 2, 3, 4. This is still +2. And 1, 2, 3, 4, 5, 6, 7. This is -2. How does this look? Well, this looks even worse to me, because if you have a pool of electrons there, then one nitrogen picked up 2, the other got, just broke even, and this oxygen lost 2. And so this does not look, actually this looks worse than that. And so having the 2 doubles is better. Well, let's work on this one, because actually we can't, well, maybe we can. Let's try this. Let's try to form another bond here. And so if I take another pair of electrons and drop them into the bond, what that does is it removes electron density from this nitrogen and gives some to oxygen. And so we end up with a structure that looks like this. Okay, now when we do the formal charges here, this is 0, 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. This is plus. And this is 1, 2, 3, 4, 5, 6. This is minus. Oh, that's looking better now. Right? Because the oxygen is not losing 2 electrons. Now the oxygen is, at least this is losing 1 electron, which would be easier than losing 2 electrons. But there's a major problem with this. Well, maybe there is no major problem. Actually, let's continue this. If I continue this, I could go like this. Now, I look at the formal charges, and finally, all the formal charges are 0. 0, 0, and 0. So all the formal charges are 0. But what's the problem there? Or is there a problem? There is a problem here. Here we have the octet rule. The octet rule has been satisfied. 2, 4, 6, 8 for nitrogen, 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for nitrogen. We double count the electrons. Here, nitrogen's, is nitrogen okay? 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Actually, do I have too many electrons? No. I guess that's right. And so the problem I have here is this. These are called expanded octets here. And expanded octets are not allowed. For oxygen, nitrogen, and all, second period elements. Third period elements, you could have expanded octets. One of the arguments that are given for this is because of the octet rule. Where does the octet rule come from? The octet rule comes from this. If we look at oxygen or nitrogen, in that shell, we have the s and the p orbitals. So we have, in fact, we have the 2s and the 2p orbitals here. And the maximum capacity of the 2s and the 2p on nitrogen or oxygen, let's pick oxygen here, the maximum capacity would be 8 electrons. 2, 4, 6, 8 electrons. Now, if you have 10 electrons, where do the extra 2 electrons go? The extra 2 electrons would have to jump to the next higher orbital, which would be a 3s. And so this would be a significant jump up in energy. So it's not stable. And so the max capacity of this is 8 electrons. And therefore, we have an octet. An octet fills the valence shell here. Some things actually expand the octet. So for example, third period and lower, there is the possibility of expanding the octet, because if we have the 3s and the 3p, that's its normal valence. So the normal valence would be 8 electrons, and we complete the octet. But if we expand the octet, they'd have to go to the next orbital. Well, the next orbital is 4s. Here. And the jump up from 3s to to 4s isn't as big as the jump up from 2s to 3s. So there's a bigger jump over there. But it's not going to jump all the way to 4s because the 4s are the outermost electron or orbitals there. Instead, it's going to jump up to a closer orbital. The closer orbital would actually be 3D, even though it's higher in energy. This is less penetrating, but in proximity, it'd be there. And so these 3Ds are empty for things like, let's see, under oxygen, sulfur. So if we're looking at sulfur, sulfur is going to have an octet. But sulfur also has the possibility of expanding the octet by making use of the 3Ds here. And so we could go 2, 4, 6, 8, 10, 12 even electrons in sulfur. Whereas oxygen, there's no 2D orbitals, and therefore it's not going to expand. The same thing for nitrogen. And so even though we can get lower formal charges, we cannot expand the octet. Expanded octets are not allowed here. And so we're stuck at an octet. If we're stuck in an octet, then this is it, and the formal charges are unstable. You know, this is like pulling electrons off. These two nitrogens pulling electrons off oxygen. You know, in a tug of war, it doesn't look very stable. And so with oxygen in the center, even though oxygen can be a central atom, and it is a central atom in a lot of compounds, it just doesn't look right here. And so maybe we could get a more stable structure with nitrogen as a central atom here. And so we'll try nitrogen as the central atom and see if it comes out better. And so why don't you draw out structures here for nitrogen in the center. See what you get, and then I'll come and draw some and we'll compare.